We will get going. Okay, so this is an ASQ Statistics Division webinar. We do these webinars fairly often. This is one of the rare times we do it only for students. So welcome to the webinar. Usually the people are muted because of the way that WebEx works. We might see if we can unmute people depending on how many we get so that you can ask questions. If you're an ASQ member, so if you are doing anything that requires continuing credits, you do get 0.1 RUs for watching the webinar, and you get an email from me as a record. So you save that email and then you can submit that when you have to put in your continuing credits. I probably will just email you the slides within that email. I'll attach the slides, but we do put slides from our webinars in the Maya ASQ Statistics Division page, and I have the link there. And we usually do record them and post them on our YouTube channel. So there are a lot of different webinars that we have done that are posted there if you're interested in going on YouTube and seeing if there's any other ones that you want to watch. So this talk is about the basics of SPC. My name is Jenny Hellrung. I host all of the webinars for the STAT division. I've been doing that for 3 or 4 years. I don't usually speak at the same time as I'm hosting, and I probably should have rounded somebody up to be the host when I was speaking so that I didn't have sort of technical issues trying to run it and speak at the same time. But I didn't prepare that, so we have to manage with me doing both. I'm on the Statistics Division member leader group, and I work at 3M. I have a degree in chemical engineering and statistics, and I've been at 3M for over 20 years. And I've worked with SPC quite a bit, seen a lot of different stuff. We won't be able to cover all the kinds of details that can come up with SPC in this topic, but in this, today, but hopefully give you a little bit of an introduction and maybe some inspiration. And you can learn more about it if it inspires you. So I am just going to stop for just a second and make sure nobody's having technical difficulties. Okay, everything looks good so far. All right. So if you have any questions come up, you can type them in the chat, and every once in a while I'll try to stop and look at those. But I can't see them real time. So I'll answer all the questions at the end of the presentation, and maybe occasionally through the presentation, I'll stop and check and see if there are any and try to answer those questions. So just if something comes up, just type it in the chat, and we'll get to those eventually. So SPC has been around since sort of the 1920s-ish, when Dr. Walter Schubert, who worked at Bell Laboratories, developed them. He was kind of the original guy. So sometimes you hear these called Schubert charts, and they're just the standard control charts. It's not a different chart. But anyway, he wrote a book in 1931 called Economic Control of Quality of Manufactured Product, but it's really all about control charts, SPC. And that's sort of where everybody started talking about it, and we're still talking about it today. It was a very good book. The concept of a control chart and SPC is very easy, but then there are lots of details that can come into it, which we won't, get into all of them today. But the basic procedure, right? And I'm going under the assumption that this is for people who don't necessarily know anything about it. So if this is, you know, too basic for you, then we'll get to some more interesting stuff in a little while. But the basic procedure, right, is that you collect data from samples from the same sort of process and you plot them on a chart. You have some control limits that you calculate and have on the chart, and you use the chart to determine if the process is sort of in control or not. So an example of a process that a lot of people have dealt with, I don't know if you guys have had to commute anywhere yet, if you drive to school or anything like that yet, but I'm sure you hear about it. And I'm sure you've had to drive somewhere before. So let's just say that I've been recording the time it takes me to get to work. And I have 20 days of data so far. And I've decided that I'm going to put it on a control chart. So here's what my data looks like so far. On average, it takes me about 40 minutes. So you can see the average sort of on the center of the chart there. You can see it's 40 minutes. That's where the green line is. And some days I'm faster, some days I'm slower. I generally don't go below 30 minutes and I don't go above 48 minutes. So if we look at some of the things that were in the procedure there, some of the words that we had, the process I'm doing is just driving my car from one spot to another, sort of the same spot to the same spot, right? And measuring the time, which is the output. My sample size is just one, right? I'm not taking different cars and doing that process. It's just one, sort of one time each time. So that's a sample size of one, but I have done it 20 times, so that's 20 different samples. And our measure of in control on this chart is going to be whether it's between the red lines, which are the control limit. And so far, all the data is within the red lines, so we're going to say it's in control. So the control limits can tell us what the natural process variability is when it's in statistical control. So that's how the limits are defined. Most processes have some chance factors that cause variation. There's always some variation in everything, right? And you can find sort of what the variability of that process is with the control limits, unless there are other causes that cause it to be not in control and to be more unpredictable. So when it's not in control, there are generally points outside the control limits and it's less predictable. The control limits are generally based on 3 sigma, and we usually mean sigma to mean the standard deviation, but with control charts, we usually use a slightly different calculation of sigma than the normal standard deviation calculation. So you'll see that in next slides. So if we talk about the commute process, some of the like natural or chance variation, right? There's lots of different little minor traffic differences if somebody gets ahead of you or not, and the number of red lights versus green lights, and maybe if you're driving just a little faster, different, a little slower one day to the next. All that kind of stuff just causes some variation, right? What we might call a special cause or something that makes things get out of control, also called an assignable cause, might be if there's a major construction delay, or you have to detour due to a closed road, or you decide to stop and have dinner or something on the way home or the way to work. Or something that was recent in our town was we had a Taylor Swift concert and we had a huge number of people in town compared to what our normal amount of people in town are. And everybody was talking about all the traffic and all the people in town. And so there was a lot of traffic due to Taylor Swift in town. That was a big deal recently. So I'm continuing to plot my my data. And the way I took it, the next point ended up being out of control. And we'll see what that reason is in a little while. And then I took another point, it was back inside the limits. And then another one, another couple more. And then I had another one that was outside of the limits. And then we're continuing along. Oh, and that was the end of my chart. And so when I looked at the comments I had done when I was taking my time, turned out that the one day was an accident that caused a big delay. And then there was a rainstorm, one of those ones where it's just sheets of rain and I had to pull over for a little while and stop, and that caused a lot of extra time. So, so I have a couple out of control spots there. And if I wanted to make sure I was always on time, right, you would try to remove the causes of those assignable causes. But when it comes to commute time, a lot of those things are not things that you can have any control over. So unless you can take a train so you're not on the road and you don't have to worry about accidents or rainstorms and I don't know. But now the chart is not in control. I have 28 samples and that's just one example. And this chart is a individual's chart called an eye chart because it's plotting sort of one point at a time and it's variables data. So we'll talk more about that chart in a minute. So you can use a control chart for sort of different reasons. You might have a process and you just want to sort of look at how it's doing and see what's going on with it. And so you might use it as a diagnostic tool. So you go back and take some historical data and see what it looks like, try to analyze it, learn where the natural variation limits are, see if there's out of control points, and try to go back and figure out what might cause that, things like that. The more useful tool is monitoring or continual improvement, where you're trying to get data more as it happens. The goal is usually to maintain process stability, but it might be to evaluate a purposeful change. So you might intentionally be making a change, hoping to improve something, and you want to evaluate whether it has an impact, and hopefully a positive impact, or maybe it has a negative impact, or maybe no impact, but you want to see what happens. And for a continual improvement, control charts are helpful because if you can identify and remove those assignable causes of variability, that can help improve the process. So if it turns out that you have, we'll go back to a manufacturing example. If you have, 6 different operators that can run the process, and one is always doing something a little bit different, and that one causes things to go out of control. If you can figure out what's happening and train that operator to do things the way everybody else does it, and remove that variability, that just improves the variability of your process. So those kinds of things can really help your process if you can do something about the assignable causes that you find. So there's all kinds of charts. We kind of separate them into 2 kinds. One is for variables data. So this is kind of the numbers data that you would normally think of versus attributes data, where it might be more like counts or different colors or categories or things like that. Numbers of patients and pass or fail or those kinds of things. So we're going to start with the variables data. So one of the earliest charts and one of the still most commonly used charts is an X bar R chart, which, we call an average range chart. The center line is at the overall average of all the data. The upper and lower control limits have formulas here. And the range is used in the formula to calculate the limits, along with a factor. So that is kind of how we use the range to do a sigma calculation. So instead of using standard deviation, it uses the range. And then the factors I'll talk about in a second. You can find those pretty much anywhere. But it assumes you take some sort of subgroup. So instead of taking one sample at a time, picture you're making a batch of, we like to call them widgets, which is just a word for something of, we don't know what they are, we're just making a bunch of stuff, right? But maybe you're making a bunch of pencils or something, right? Some bunch of parts. And instead of taking one and taking a measurement, you're going to take 3 or 4 and take a measurement. And then every time you go to take a sample, you'll take 3 parts. And so your subgroup size is 3. And so on here, you would plot the average of those 3 on the top chart. The bottom chart is the range chart. So on the bottom, you would plot the difference between the maximum and the minimum value in that subgroup of 3. So hopefully that makes sense. And the center line for the bottom one is just the average of the ranges then. So, so it can show you where your average is at for all the parts you're looking at, and then it shows you the difference in the sample. So it's a sort of an estimate of the variation in your samples below there. So if you make batches over time, this shows you how you're doing over time, right? And this looks pretty stable. Looks like the average doesn't change that much. And it goes, up and down around the mean, which is good. If it continued to go up or continued to go down, that would be a bad thing unless you were doing that on purpose, right? Because usually there's a target that you're trying to stick to. So that's the kind of stuff we're looking for. Or if you had one batch that was really big or really small, what are those pencils going to look like, and why would that be different, right? So we're going to continue going here. So the next one is the individual's moving range chart. This one is where you have just a sample size of 1. Otherwise, it's very similar, right? So when you take a sample, you take just 1 at a time. So this works with all kinds of different types of data, where you have manufacturing data and where you have other kinds of things like our commute time, where maybe it doesn't make sense to have samples. This one comes in handy. And then you don't have a range in samples now, so we have what's called a moving range, and that's just the difference between consecutive points. So when you take your first sample and then you take your second sample, you have to wait till you get your second sample to get a data point for the range, and it's the difference between the second point and the first point. And it's just the absolute value of those differences. And so you can just plot those. Those get plotted on the bottom. And then that moving range is used to calculate the limits for the upper chart. That's what gives you your sigma for your 3 sigma limits. Again, it has these factors. And these factors help you to change those range and moving range into sort of your sigma calculations. And these can be found in all kinds of statistical books and quality books and all over the place on the web. So you can find those all over the place. Plus they're built into all kinds of software. So if you're using software, it'll have those already in there and you won't need to know the factors, but they're very easy to use if you want to do a control chart on a spreadsheet or something and you don't have a statistical package. So you don't have to have a statistical package to do a control chart. You can find this information and do it without that. And so the N is just the number of samples. And as long as you know the number of samples, you just go across the row, read off the factors that you need, and you can calculate all those limits. All right, I am going to show you an example that uses another chart. And we're going to see if we can get the YouTube to show. Sorry about the ad.
Tape was invented in 1925 as a painter's masking tape for auto body shops. Transparent tape designed to seal the cellophane wrap by string. Then tape was introduced as a household item. Idea just stuck. Rolls of plastic film called polypropylene are on their way to becoming shipping tape. Go on a machine called the unwinder. Workers then position a strip of adhesive splicing tape along the end of each roll. This will enable them to connect one roll after another. Interrupted feed to the production line. Now watch closely. Once a roll unwinds completely, its end sticks onto the splicing tape at the beginning of the next roll. Once that roll's unwound, its end will stick to the beginning of the and so on. The tension adjuster ensures that the machine pulls the film.
Okay, I love how it's made. That was not the official how it's made. That was from International Paper. But I work at 3M and we also make different kinds of tape at 3M along with films and all, you know, lots of other stuff, car wraps and all kinds of different things that are made in these big rolls. So when we talk to people outside of 3M and we talk about a roll of tape, people sometimes think about a little Scotch tape roll, but sometimes we're talking about like a 6 foot wide sort of, you know, 3 foot diameter roll of tape. So sometimes it takes a good picture to get that across. So I just thought that was maybe useful. And so in this example, we're going to take 3 samples at the end of each roll. And again, this is one of those big old rolls. And we're going to measure caliper or thickness on those samples. And then we're going to plot those on a control chart. And so I took 3 samples. So I'm going to plot them on an X bar R chart. And it looks kind of funny, right? Because the control chart limits are supposed to kind of surround the data and look like what the sample range chart looks like, but the X bar R chart looks odd, right? Because more of the data is outside the limits that are inside the limits, and that's not the way it's supposed to look. So there's a reason for this, and there's a chart that can account for this. The reason for this one, and I just think it's an interesting example, so stick with me, but if you think about it, because this is such a big roll, right, the variation within a subgroup is sort of across the roll this way, and then we're plotting from roll to roll, which actually, when you think about a continuous process here, is actually going sort of down the roll from roll to roll and over time. And so it's sort of from one sample to the next is a different direction than from within a role. So those can actually have different factors that affect the thickness. So there's a bunch of engineering things that can go into that. You know, it's when you get into the processes of making this stuff, but the fact that there can be different factors within a sample versus from sample to sample is not that uncommon. It can happen in like injection molding and other kinds of processes. And you can think of other examples maybe, right? Where if you were going to sample different classes, maybe you take a science class at a high school, and you're going to ask some questions of a group of people in that same teacher's science class every year. Well, I'm guessing the year that there was a pandemic, you're going to get different answers than maybe other years, right? Just because of all of the things that were going on with the pandemic. Even if you're asking just science questions, they may be behind due to classes being canceled for a couple weeks or things like that. So there are factors that can affect things, but the people that are in that class together, those answers might be more alike than from class to class, right? Because things that happen that year in class, those people are going to have more similar answers than from year to year, if that makes sense. But anyway, the way that you can account for that when you have sort of those different sources of variation is a 3 chart, which is really a combination of the 2 charts we already looked at, the individuals and the average chart. And you can call it multiple things, right? It's one of those ones that nobody ever decided on a name for. So we call it a between within, an IMRR, IMRS, X-bar, MRR. So lots of different things you can call it. But the 3 charts are what I would call sort of an eye chart of the subgroup averages. So you're still plotting the subgroup averages, but you're using the calculations for the limits like those averages are individual data points. And then there's an MR chart of the subgroup averages, and then there's a R chart of the range within the subgroups. So basically you have these 3 charts, and then the top chart shows it over time, and you can see that now most of the data is inside the limits, although there still is some data outside the limits. And then the middle chart shows roll average variability, and the bottom chart shows within roll variability. So this is within the sample at the bottom, and this is the moving range of the subgroup averages. So it's how that variable changes from group to group. And you can see that on the top group, the data points aren't completely random, right? There are some sort of sections, and that's because they made several jumbos at a time, and then they stopped. And then when they started making the product again, they were in a slightly different spot. And then they made a few more and they stopped. And then came back later and made some more and started back up again. And again, we're in a slightly different spot. So there's some work they could do to improve targeting their thickness to be closer to their target. So they start sort of at the same spot every time. So any control chart would help show that pattern there. And that's something they could improve on. So those are all the variables charts I'm going to show right now, but there are lots of other specialized charts. But I think the IMR and the X-bar are really the most common charts. I'm going to just briefly show an attribute chart, but not go into a lot of detail on those. But there are attribute charts for different kinds of things. And there's more than this as well. There's lots of other kinds of charts. So if you have a specific case and you can't find a chart for it, if you Google, you can probably find something, or you can ask an expert. But I wanted to show something other than a manufacturing example. This is more of a healthcare example. This is a control chart for surgical site infections. This is real data that was published, and I stole it to use here. So the copyright and all the information is down here, but this is the infection number that they're publishing here. So they collected data from times when they had 45 infections, and what they're plotting is actually the number of cases between infections. So the bigger the number here, the better, right? Because that sort of is the longer you went before you had another infection. So you want those numbers to be big. So they were going along and collecting data, and then they did a change in the wound cleaning protocol, and you can see that they continued to collect data, didn't seem to have any effect. They then did a change in the shave preparation technique, and you can see that after that there were some out of control points. So that probably was helpful, especially in addition to, that probably made the wound cleaning protocol more helpful, if you ask me, although I'm not the expert in that. But probably that made the wound cleaning more effective. Anyway, they did get some much higher numbers after the two of those. So that looks like that was effective, and maybe changing the average number after that. So it would be interesting if they continued to collect more data and then maybe tried to do recalculate the average and control limit after they made this change and see where they were at. I think that would have been interesting, but this is actually, because this is count data, they used a C chart. C stands for count. We're not, statisticians are not always really creative, but you know, so C is for count. The center line is at the average counts, right? You add up all the counts and divide by the number of samples. Here you just need the average counts. You take 3 times the square root of the average counts to get the upper and lower control limits. Usually the lower control limits I think are going to be 0, but if you had really high counts, you could calculate a lower control limit as well. So that's how that one works. And that's all I'm going to show on the attribute ones, but there are other ones. There's proportions and all kinds of different charts, but so they definitely exist. And I want to talk a little bit about run rules before we stop and answer questions. Run rules are using criteria other than just being outside of the limits to determine if it's in or out of control. So this is some data that I just looked at. This is viscosity data from batches of liquid material made over the last year. There's no points outside the limits, but if I look at it, it sort of looks like it was higher in the first half of the year and then lower in the second part. So I don't really like that. I would rather it be sort of centered over the average the whole time. And that's where you can have you can add run rules and it would catch that sort of thing generally. And these can be worded all kinds of different ways. This is worded sort of weird, where like zone C is 1 standard deviation away from the mean. Zone B is 2 standard deviations. Zone C is 3 standard deviations. So that's kind of worded with just zone A, zone B, zone C, but that's what that is. And you can see there's lots of rules here. There are other rules. There's a set called the Western Electric I think there are other sets. This is what it looks like for some of those. So you can sort of see like 9 points in a row beyond. In row zone C or beyond, a lot of times that's just worded on one side of the control limit or not, or the other. Mine didn't quite have that. My previous chart here, it had 8 on one side of the, I think I counted here and I got to 8. I didn't get to that one. But I did apply a couple rules and we'll see what it got to. But you can see there's like 14 points alternating up and down. All kinds of different kinds of rules here. 2 out of 3 in a row in zone A or beyond. I think I applied that one. That's a pretty common one. So different software can have different rules, different sets of rules, different combinations. Certain industries may have certain standard sets. So if you make product for semiconductor or aerospace or automotive, sometimes they have a specific set of rules they want you to use as a supplier. So sometimes there are lists there. Every time you add another way to determine it's out of control by adding another run rule, you increase the risk of false alarm. So you need to be careful not to add, you don't just go turn them all on or you'll be having signals all over the place and it won't necessarily indicate assignable causes all the time. And it'll just get create havoc in my opinion. So I would say to limit to 4 or less, unless you're required to have more. I'm not sure if there's a specific standard anywhere to limit to 4, so I'm just putting that this is my personal opinion. And then you have to be careful because an assignable cause when you're using the run rules doesn't necessarily happen where the out of control point is. It's obvious when it's just outside the control limits that the point that's outside is where the assignable cause is, but with the run rules, that's not necessarily the case. It's also, this last sentence here, the number of out of control points is not necessarily equal to the number of assignable causes, right? You might have one assignable cause that generates multiple out of control points. There may be a couple assignable causes and multiple out of control points, and it gets a little harder to tell what's happening, but they can be useful to pick up certain trends that don't happen, that don't show up in the out of control, outside the limit one. So I was using software, and so I showed you here what was available, and my software added, the way it described things was really odd, because you could change like the number of standard deviations from the center line. I'm gonna have 12 standard deviations from the center line be it. Yeah, that's crazy. Some of these are standard and you shouldn't change it, but anyway, I added 3 more run rules. This one's the standard one, 3 standard deviations from the center line. And so I added, this is 2 out of 3 standard deviations from the center line on the same side, and 8 points in a row greater than 1 standard deviation from the center line. And you can see anyway here, 5 and 6, which is these 2 are the ones that that signaled. So it's 5 points greater than 1 standard deviation from the center line. So you can see each of these times it had more than 5 points on one side of the center line that were more than one standard deviation away. So anyway, you can, with this change, it didn't signal when it changed to the bottom down here, but when it shifted and went lower over here, it made the top part signal. So I think the assignable cause is actually when it changed at somewhere between, 11 and 15, there was a change and it dropped, but that made it signal sooner than that. So again, where it signals and where the change happens doesn't always align exactly. So what do you need to have to be able to do SPC? I have a young teenager, and I've been having to help her do math lately, before the school year ended. And I assume at some point they let you use computers, but they're still making her do all her graphs and stuff on paper. And so that was kind of fun. I haven't had to do that in a while. But you could do these on paper if you had to, right? You don't need to have fancy software. But if you do, there's tons of stuff out there, right? There's free stuff. You can do it with a spreadsheet and put reference sort of lines that are the upper control limit. It won't make your points turn colors when you go above it, but you can deal with that. There's Excel add-ins. There's you can use Power BI and sort of program it. There's lots of stuff out there that already exists that will do real time and offline and all kinds of different stuff. And you don't have to be in a certain spot in your data analysis to be able to do SPC. You don't want to wait till your process is in control or that you have the perfect software to be able to do it, because just making the charts, you can learn a lot from it. Couple other points, how you take the samples is important. We didn't really talk about that a lot, but having good sampling is important, and sampling can be its own class. And we're not going to get into all of that, but taking good samples is important. 3 sigma limits is sort of the basis of the charts. You don't want to do a different number of sigma. And there's just tons of resources out there to get more information. It's all over the place. If you have any issues figuring out where to go, you can contact me and I'd be happy to help you find stuff, point you to stuff. Here's my email. And you will be getting an email from me, just like I said, for the credits and the slides. And now I am going to stop sharing so that I can look and see if there are any questions here. So what do you guys think? Anybody want to write a question in the chat? I kind of talk fast. Anybody have any comments? I hope that was somewhat interesting. I will be sharing the slides. You'll get it in the email. I see the question, can we review data in real time? Yes, some of that software was real-time SPC. A fair number of that. And you can even, like Power BI, you can program it to go that way. A lot of the Excel add-ins, you can run macros to make it go real time. And then a lot of those other ones are just intended to be real time. But yeah, if you just plug like real-time SPC into Google, you'll be able to find lots of SPC packages. And if you put free in front of it, you can find lots of stuff there too. And I think there are some like online ones that you can plug it into the website and it'll make real-time charts for you. There's lots of really expensive ones. So depending on what it is you're trying to do, but there are some free ones just to get some basic ones. Other questions? Common mistakes while applying SPC. There's a few. One is to change the limits on the chart, right, to like two sigma, 2 standard deviations. You're going to get a lot of out of control points if you put it to 2 standard deviations. Sometimes people think if I make it tighter, it'll be better. I'll find more stuff. But you'll get signals that don't mean anything. And then you'll be searching for reasons for that, and that there won't be reasons, and that'll be frustrating. So that's not a good way to go. The other thing in when you have like a manufacturing example, changing the control limits for like specification limits is not a good idea. And people sometimes want to do that. And the specification limits and the control limits are both very useful information, but they are used for different purposes, right? You can be in spec and in control, which is the ideal situation. And then there's all the combinations that you can get that are not ideal with those control limits and specification limits. But you don't necessarily want to show them on the same chart when you're trying to monitor. Sometimes when you're diagnosing, you want to show them on the same chart, but you don't want to replace the control limits with the specification limits and try to call it a control chart, because that's just not the right thing. And then there's some limit calculations and stuff, but I wouldn't worry about that so much if you can, as long as you're trying to learn something from the charts, there's ways to get around it. Oh no, here's the question. I just always wanted to confirm the control limits are always within specifications. No, that would be great. They are not always within specification limits. The process will put the control limits wherever it feels that it goes, and it doesn't know where the spec limits are. So you hope your control limits are within your specification limits, but it won't necessarily end up that way. It's a very good question and it's a question that comes up a lot, but if you have any product that is outside specification once in a while, then your control limits are probably not within the specification limits. So I am not familiar with the software Red Zone. So I would have to look at that. If you want to ask me that on email, I'd be happy to look that up and let you know. There was a question about Red Zone and whether that can do real-time SPC, but I don't know the answer to that. And there's a lot of things around like fixed limits versus floating limits and things like that, but that's sort of more than we're going to get into today. But yeah, there's lots of resources out there that you can find and learn more about SPC if you're interested. So thanks for attending. I'll send you an email with the presentation and your RUs, and I hope you found it valuable. And when you become full members of ASQ, you can join all our webinars, but the webinars on YouTube are available now. And you can join all our webinars now anyway, but you might be too busy with school. But we have webinars pretty regularly, at least monthly usually. So you're welcome to join whenever you want, if you find the time. And I'd be happy to see you again. Thanks. Bye.